welcome everybody in the audience today. We have 70 attendees so far and counting to the first webinar, the Combustion webinar of this semester's new series. The opening talk for the series for this semester is to be given by Nicolas Noiray of ETH Zurich. Nicolas is one of the rising stars in the field of combustion and thermoacoustics, and is going to be telling us about nonlinear and stochastic thermoacoustic dynamics in combustors during steady and transient operations. Nicolas has gotten his PhD in 2007 from École Centrale. He worked for a time with Alstom afterwards, and then moved on to ETH Zurich, where he's now a very successful younger professor to start on the thermoacoustics of turbulent flames for gas turbine applications. So with that, I'll hand the floor over to you. But first, I'll just remind the audience, if you have any questions, just put them in the question and answer box at the bottom of the screen or the chat session, and we'll read them out at the end of the talk one by one so that we get a chance to answer as many as we can in the time we have. So with that, take it away, Nicolas.
Thank you very much, Isaac, for the kind introduction. And hi, everyone. I'm very glad to open this semester of webinars, and today I'm going to talk about nonlinear and stochastic thermoacoustic dynamics in combustor during steady and transient operation. And on this slide, you see the experimental setup which we have at ETH, and which is modular enough to allow many type of different configurations. So there are different modules, and then we can exchange the blocks. And you see here a single stage configuration. But during my talk at the end, I will talk about sequential combustion in this system. So today, the topic is about the sound of flames and about thermoacoustic instabilities. And these thermoacoustic instabilities, I will focus on the situations when they happen in gas turbines for power generation and in aeronautics. And these instabilities, they result from the feedback loop between the flame dynamics and the unsteady heat release rate, and the chamber acoustics with the acoustic velocity and acoustic pressure. And this feedback loop can lead to high amplitude thermoacoustic limit cycles. And this dynamic pressure fluctuation or acoustic pressure fluctuation, the amplitude is so large that they induce damaging structural vibrations. And ultimately, in the bad situations, they lead to catastrophic failures of the systems, and this is really to be avoided at all costs. And nowadays, there are more and more a major obstacle to the clean combustion of different fuels. So not only the standard fossil fuels, but also synthetic fuels like hydrogen. And I'm going to illustrate with these slides what a thermoacoustic instability is in a single can combustor. So this is high-speed chemiluminescence of one of the configurations of our test rig, and it's an air-methane mixture which is applied, so fully premixed configuration. And we've done some laser-induced fluorescence and some OH leaf in this setup. And I will also, again, come back to this point a bit later. But let's say that for the introduction slides, I would like to mention that depending on the operating condition in a gas turbine, the flame topology is changing. And this is illustrated here for this particular atmospheric test rig, where we go from a V-type turbulent flame to an M-type turbulent flame when we increase the fuel mass flow for a given air mass flow. So basically, we increase the equivalence ratio and the thermal power at the same time. And this leads to this transition in flame topology. So you have the instantaneous peak here on top and the average one at the bottom. And on the way, you find thermoacoustic instability. So this is a map of the acoustic amplitude, the RMS value, and you can also look at each thermal power, the statistics of the amplitude of this acoustic oscillation. So you take the envelope of the acoustic pressure signal and you look at how this envelope behaves, and it has some randomness, and looking at the statistics, you can plot this kind of contours. And if we look at these three operating conditions here, the first and the last one, so the leanest and the richest ones, they exhibit rather low thermoacoustic amplitudes, and they do not exhibit a thermoacoustic limit cycle, which is not the case for the intermediate condition, where you have this high amplitude acoustic amplitude, and you see here in the acoustic spectrum the presence of this significant peak, which is the signature of a limit cycle of one of the longitudinal acoustic modes in the chamber. And if you look at the with a photomultiplier at the light intensity from this fully premixed flame, you will see that the peak that you saw in the acoustic signal is also observed in the power spectral density of the flame chemiluminescence, and only at that condition. At the other conditions, you have a rather flat power spectral density. So these thermoacoustic instabilities, they are really problematic. And the problem is that there are different mechanisms, or many mechanisms, which can cause these instabilities. And this is the topic of intense ongoing research at many places in the world. And what I'm gonna focus on today is about the transient operation effect on the thermoacoustic instabilities for different system architectures. And we will see different kind of phenomena, and what I'm gonna show are recent studies that we've done at the lab, and to illustrate the diversity of the thermoacoustic phenomena that we get when we do this kind of transient operation. And this transient operation, they are really relevant for aeronautic applications when you do maneuvers and you have rapid change of the load of the engine. You have to account for these transient effects in your thermoacoustic analysis. So the agenda of today is with different examples. So we will start first with the supercritical Hopf bifurcations in a single can combustor, so the one that I was using in the previous slide. And I will talk about how to dodge bifurcation, so how to go through without feeling the high amplitude or getting the high amplitude thermoacoustic limit cycles. And I will talk about hysteresis that you can get due to thermal state of the combustor and the transient thermal state. I will talk about subcritical Hopf bifurcation in this same kind of combustor. So then you have other effects that come into play. And especially we will talk about bifurcation delay and intermittence. Then I will switch to a more complex combustor architecture, which is an annular combustor architecture, which is very typical for aeronautic applications and also for power gen gas turbines. So the intermediate size gas turbine and the small size gas turbines are often made of annular chambers. And there I will focus on symmetry breaking of the thermoacoustic system, on intermittence again, and on hysteresis and beating modes in this type of annular geometries. I will go then to sequential combustors, which is a topic which we investigate at the lab in the frame of several projects. And I will talk about synchronization of longitudinal modes, about transient thermoacoustics during blow-off of the first stage, or about transient associated to the presence or not of a plasma. So how we can control thermoacoustic instability with nanosecond plasma discharges. And I will start first with the supercritical bifurcations in single can combustor. And the work that I will present here, most of it has been performed with my PhD student Giacomo Bonciolini, who defended his PhD 2 years ago. And so with Giacomo, we saw many interesting things. And I start with the dodging of the bifurcation. So we are back to the same system that I was presenting before. And what you see here is that you have a hill in between. So it's linearly unstable. The thermoacoustic system is linearly unstable here. And when you run at this air mass flow in the system, then you are attracted to this limit cycle. And the question is it possible to ramp fast, to go to the set point in a fast way and dodge the bifurcations? So there are two bifurcations, one here and one here. And intuitively, we could say that if we are fast enough to change the bifurcation parameter, then the system will not be repelled sufficiently fast toward the attractor, and then you can get to that point. And we will see that in this first example, this is indeed the case, that the intuition gives you the right the truth. And but what we've done is that we went with the modeling of this, and this is what I'm going to show now. So what we've done experimentally, so these are experimental data. So we have done different ramps and different ramp duration, and we switched from an air mass flow of 12.5 grams per second to 20 grams per second. So a very significant change of the air mass flow. And you see here the change of equivalence ratio, which is associated with this rapid change of the air. And we've done several ramps. So this is the fuel mass flow, and this is the acoustic pressure signal that you get. And we've done this many times to get the statistics during the ramp. And so these are 3 examples. And collecting all the statistics, what we observe is that in contrast with the statistics of steady operation, so here each column corresponds to a fixed operating condition at a given mass flow. If we do it in a transient way, and if we average that, what we see is that statistically at the instant where we are at this mass flow, we will not be at this amplitude, but around this amplitude. And if we ramp faster, so if we have a faster ramping time, and here we are talking about 0.16 seconds, and here this was a ramp of 1 second to nearly double the mass flow. Here we don't reach this high amplitude oscillation of about 15 millibars. So this is a success. And what we've done afterwards was to try to find low-order models of this. And in this situation, is the simplest formulation is to simulate the thermoacoustic mode as an oscillator, a self-sustained oscillator. And depending on the equivalence ratio, the system will be stable or unstable, which means that the damping will be either positive or negative. So if you have a negative damping, that means that you will be producing acoustic energy, and you will be attracted to a finite amplitude. So I will not go today too much into the equations. I will more illustrate the phenomena that we have looked at. But in all these studies, we tried to incorporate the nonlinear dynamics and the stochastic phenomena that are observed experimentally. So if we do here identification of the system parameter of this surrogate model, then we see that here we have the linear growth rate, the damping here, which change sign at this air mass flow, and we approximate it with this curve. And once we've done that, we can also incorporate these fitted parameters into another equation, which defines the time evolution of the acoustic amplitude statistics, of the probability density function of the acoustic amplitude. So this is what you see here. So you can compute how this will change with time when you change the system parameters. And this is the Fokker-Planck equation governing the amplitude of the thermoacoustic system. And so here we see that the system identification is rather successful because we reproduce well this transient phenomenon and the bifurcation dodge. Here a few words about the Fokker-Planck equation. There is a drift of the amplitudes, which is associated to this transport equation for the probability density function, and a diffusion term here, and this diffusion governs the spread of the PDF. So once we have done that, we can make use of this type of model to do a preliminary risk estimation. So knowing the parameters, we can try to see how fast you should ramp to not exceed, let's say, 7 millibar, because you know that your mechanical system will not resist, will not survive amplitudes which are above. And so doing that, you can explore it with the Fokker-Planck equation, putting an absorbing boundary condition, and with this absorbing boundary condition, you can obtain the probability of not having exceeded this amplitude, and this is represented in a map here, and you see that depending on what's your maximum growth rate that you will encounter in this type of system, you have to be very fast so the speed at which you have to be is this Y scale here. And so if you are in the white region, that means that you were too slow and that you will statistically be sure that you will exceed this amplitude. So you have to be in the blue here to be sure that you will dodge these bifurcations and stay at low enough amplitude. So now I switch to another example where we slightly modified the system. So up to now, the system was with a quartz round chamber of 100 millimeter diameter. And now we switch to 70 millimeter diameter. So the flame is more confined. And this is the PLIF images that I was showing at the beginning. And instead of doing a technically premixed injection, so with natural gas being injected here, what we do is the fully premixed configuration. And so in that case, so these are what I was showing before at the beginning. You have these 3 states. So this is resembling very much what we have seen before, but here something different happens. So let's look first at steady state operation. So when we are at here 28 kilowatts, we have a V-type flame. So this is a high-speed OH PLIF, and we see that the outer recirculations are not are filled with fresh mixture. Then when we ramp the thermal power and go to 34 kilowatt, then the quartz tube gets hotter, and this hot wall helps in getting the hot products trapped into the outer recirculation zone. And in that situation, we end up with an M flame. And these two flames, the V and the M flames, both of them, they have rather low amplitudes. And in between, there is this high amplitude thermoacoustic peak, which correspond to the transition state where you will start filling up periodically these regions, because the wall is at a sufficiently high temperature, allowing the periodic excursion of the flame inside the outer recirculation zone. And so this is a big difference compared to the previous situation, because in the previous situation, the flame topology was not changing when the air mass flow was ramped. While here, when you ramp the thermal power, so you ramp at the same time the air and the natural gas, you have a significant change of the flame topology due to the thermal state of the system. So this is explained or summarized with this cartoon here. You have here the stability, which depends on the flame topology. And here, when we are in this intermediate thermal state, you have the possibility of the flame branch to attach to the outer rim of the burner outlets. And so what we've done is that these were, let's say, results that you can obtain by looking at steady state. And what we've done afterward is to do ramps again. And this is here shown on this slide. So we did again 1 second ramps. But the thing is that once we ramped, we entered the region of thermal power where we should be unstable. So we start becoming unstable, but then we end up to the high thermal power, but the walls are not yet hot. So the system is still thermoacoustically unstable with very large amplitude. So you don't instantaneously go back to the low amplitude that you would expect in a steady state. And this thermal transient is very crucial in this situation because it will impose a certain duration to the high amplitude thermoacoustic limit cycle. So this will govern how bad your mechanical system will be loaded. And so we've done some further analysis. We've looked at the light intensity in the outer recirculation zone. And this, you can see that beyond this point here, you start periodically filling up the outer recirculation zone. And this is at the frequency of the thermoacoustic oscillation. So if we would zoom, we would see that, we would see that this is oscillating periodically at the acoustic frequency. So we are periodically changing very significantly the heat release rate, because anytime we ignite the outer ring, this makes a sudden increase of the heat release rate, and which is, let's say, coupling with the acoustics. So here again, we can model that and express the influence of the thermal transient in the system. And again, we can do system identification and run the Fokker-Planck equation with this transient change of the system. And this is reproducing very satisfactorily the experimental observations. So Now I switch to another system. So it's still a turbulent swirled premixed flame, but in that situation the burner is a bit different, and you have a subcritical half bifurcation, which means that when you increase the thermal power, you will at one point suddenly jump to the limit cycle. So it's not a hill that you will have. You have a sudden jump, and then if you ramp back, you will follow this kind of hysteresis, and this is what you get. So this is a picture that you can have if you are changing the system parameter in the quasi-steady way. So you are going very slowly up or down, and the arrows indicate where you will end up in your thermoacoustic system. But in a turbulent combustor, what we have seen in the previous slides is that you have turbulence, which is inducing a turbulent component to the unsteady heat release rate. And this unsteady heat release rate, the turbulent component, induce a broadband acoustic forcing to the thermoacoustic system. And this broadband acoustic forcing explains why you have, let's say, a probability of having a certain amplitude at a certain time. So this is, let's say, the PDF of the acoustic envelope that I was talking about before. And so this is what we obtained when we changed the equivalence ratio and we increased it progressively. We see that at low equivalence ratio, the system is stable. And then when we increase it, we have these bursts of acoustic, high amplitude acoustic limit cycle. And this is because we are getting close to this region. And from time to time, we have, let's say, noise-driven jumps between the two attractors. So you are attracted here, but also by this point here. And this is the turbulence which is allowing this intermittency. And the more you get into this intermediate region, the more frequent become the high amplitude. And then at one point, you are ending up with this limit cycle. And so here again, what we've done is to look at transients when we are ramping up the mass flow. And in this situation, there are two things that happens. First, depending on the rate at which you ramp, you will stay longer. There will be some inertia to some kind of, maybe I shouldn't call it inertia, but let's say that the system will stay close to this attractor and will jump after a certain time to the equilibrium. And so the ramp rate will govern how fast you will end up to this point. And this is also very important in a practical situation. If you have flames in an engine which exhibit this type of behavior, it's very important to account for that when you are setting the maximum ramp rate, because you may not feel it until you jump to a very, very high amplitude. While if you are going slowly, and this is also intuitive, you will not face the worst consequences. And here again, we can compute with the Fokker-Planck equations some statistics about at which rate, ramp rate, a certain amplitude will be reached. So this was about the single can combustion systems. Just looking at the time. Now I switch to annular combustors. So this work has been done in collaboration with James Dawson and his group at and his PhD student Thomas Hindlekoffer at NTNU, and with my PhD student Abel Forbollier. So these results were obtained for this NTNU annular combustor. And there, what we've done is we operated it with hydrogen and methane, and for different fuel blends or fractions of hydrogen and different thermal power. And in the first slide, I will focus on a situation where the thermal power was fixed to 72 kilowatts, and the equivalence ratio was changed between 0.475 and 0.625. And here we see that when this equivalence ratio is increased, we have a supercritical Hopf bifurcation. So it starts like a hill. So this is the acoustic amplitude in the system. Before that, we have only a resonance, which is sustained by the broadband turbulent combustion noise. And beyond this critical equivalence ratio, we have limit cycles, so finite amplitude acoustic thermoacoustic waves. And these amplitudes, they correspond to the peak here in the spectrum. So we see here that for these different equivalence ratio, we have the amplitude of this azimuthal mode, which is growing. And for the yellow one, we are still linearly stable. So this is this case here. So the amplitude is still, let's say, moderate. And beyond this equivalence ratio, we get to the very high amplitudes. And this corresponds to spinning and standing waves. And this is what is interesting with these annular systems. We don't have a standing mode established as we do in a single annular, in a single can. We have the possibility for the waves to continuously propagate along the ring, or to sometimes fix at some position. And this is the different type of thermoacoustic modes that we can obtain. So we can obtain spinning modes, standing modes with fixed nodal line position, or mixed modes, which are combination of spinning and standing modes. And recently, so there will be a few equations in this part. Recently, a new projection of the acoustic field has been proposed. Is based on 4 state variable, the amplitude, which I was showing before, and 3 angles, the nature angle, which defines if it's a spinning, a standing, or a mixed mode, the antinodal line position, which is governed by theta here, and phi is the temporal phase drift. And basically, what you can do at any instant at any instant when you observe your thermoacoustic mode, you can associate a certain state, and this state is defined by these 4 state variables, and you can represent them in a Bloch sphere representation. And there is a certain amplitude A, and then you have your vector, your state vector, pointing either in the northern or southern hemispheres, which correspond to either mixed modes, whose spinning component is spinning clockwise, or mixed mode whose spinning component is spinning counterclockwise. And at the poles here, this is a pure counterclockwise spinning wave. And here at the south pole, it's a pure clockwise spinning state. And at the equator, you have standing modes whose nodal line is defined by the position where you are pointing. So I keep in mind this representation, because this is what we use here when we try to depict statistically how the mode is when you are at this equivalence ratio. So when you are close to the bifurcation here, you have these state variables which are evolving like this, and statistically you will be here at around the equator with these 2 lobes which are defining the probability of being at a certain state. So these are mixed modes close to standing modes. If you go higher in the equivalence ratio, then you get another type of distribution. Now you have 2 islands here. one for mixed mode with counterclockwise spinning components, and here with clockwise spinning components. And then if you go significantly further, then you are nearly purely spinning state. So these are the raw data during 100 seconds. And if you zoom in, these are oscillations at about 1 kilohertz. You have this quasi-pure spinning state with the state probability being close to the South Pole. So there are symmetry breaking here beyond a certain equivalence ratio, then you don't switch to the other spinning direction due to the turbulence. You are stuck in here. And there is also here a preferred angle, no matter which equivalence ratio you start your combustor, you will have a preferred direction. And this, we explained it, that the tiny imperfections in the systems, they will be magnified in the vicinity of the bifurcation, which is such that any system, even if it's designed nominally to be nominally symmetric, as it was in the present case here, you cannot avoid to have this locking, this preferred direction, this magnifying lens effect of the slight asymmetries of the system. So we modeled that also with the Fokker-Planck formalism. I'm skipping these slides. We do system identification to identify the parameters of our model. We show that, yeah, what I depicted before, these jumps between counterclockwise and clockwise component of the mixed mode are possible when the noise intensity is sufficiently large to escape from this attractor and return to it. But then beyond that, you have this spontaneous symmetry breaking of the state, and you don't jump anymore to the other one. So the state PDF is not anymore symmetric. So this is the simulations, what we obtained. We can also predict with the Fokker-Planck equation what the system would do if we augment asymmetries or if we augment the noise in the system. And we can also run time domain simulation of this low-order model. So this is a wave equation. I'm going a bit fast here because I would like to talk about the sequential combustor. But here you see experimental data and model simulations of these state variables. So here, note that this is 6 seconds of the evolution of these state variables, but the acoustic oscillation is at 1 millisecond. So any acoustic cycle is very fast compared to this fluctuation that we see here. And here we see, for instance, that the mode will start spinning left and then it's go to spinning right. And there is also a statistical preference for the clockwise spinning direction in that particular situation. Then another thing that we've seen in this annular combustor is that we can have beating modes. So in that situation, you have something which is periodic. So there is still some stochastic effects in the system due to the turbulence, but you have this very periodic beating, which correspond to alternation between standing modes, spinning modes in the two directions. And in that case, the state PDF can be represented like this. And here again, we looked at transients, and we see also some very funny phenomena. So we see that in the situation where we lower the thermal power of individual burners, so each of the burner is a 4 kilowatt burner, and there are 12 burners like this. You see the flame here with a phase averaging. So it's a little turbulent flame with a phase averaging of the acoustic cycle. If you ramp up, you will see these beating modes appearing. But if you ramp down, they stay all the way down until suddenly they stop. So it's you have a completely different nonlinear thermoacoustic dynamics taking place. So this is very intriguing, and we looked at that in a recent combustion flame paper. So now I go to the last part of my presentation, and I try to be concise. This is about sequential combustors. So sequential combustors, we've looked at it at the lab because these are very convenient architectures for fuel and operational flexibility. And in particular, for burning hydrogen in a huge gas turbine, this is very convenient because you can, let's say, change the fraction of hydrogen in your blend natural gas hydrogen. Or you can change the two stages of the combustor such that the performance is maintained with low emissions while increasing significantly the hydrogen fraction. So how does it look? There are two combustors. In between, you have air from the compressor, which can get inside to dilute the hot products of the first stage. So you bring the temperature down to about 1000 degrees Celsius. And this is a key aspect of the concept, because this 1000 degrees, it's sufficiently cold such that when you inject your fuel in the sequential stage, it does not immediately ignite. You have autoignition times of the order of a few milliseconds, and the residence time, which you get from the burner velocity and the distance between the combustion chamber and the fuel injection, this residence time is more or less equal to the autoignition time. And during that time, you are mixing well, and the combustion that takes place in the sequential stage is a combustion that is happening in a rather homogeneous environment. So therefore, you don't have the hotspots leading to high NOx formation, and it's therefore very important to have this cooling here. Now I go back to the thermoacoustic part of this system. So this system is more complex than a single stage combustor system. And therefore the thermoacoustics is also more complex because you don't have only acoustic interaction between the two flames, but you have also equivalence entropy waves, which can also couple the two stages. And in particular, if you have fluctuations in the first stage due to acoustics, so periodic oscillation of the heat release rate and the mass flow, together with the one of the dilution, then you are going to modulate the autoignition time and modulate the sequential stage. So this is getting really complex, and this is what we try to investigate, what we investigate at the lab. And one thing that we have looked at was the coupling between two modes of the system. So the first two longitudinal modes. So we made, we found operations when this kind of situation happens. So this is the sequential combustor that we have. We have the first stage. So this is a version that we were using 2 years ago. Now we have a more compact sequential combustor, which I will show a bit later. But we had in the past a swirled turbulent flame in the first stage. And here you see the autoignition flame in the sequential stage, and the injection of the gas is done here where my mouse is pointing. So I'm going. So this is when it runs. So and what we've done some high-speed chemiluminescence of the different of the two stages, the first and the second stage. So they are not as close as we see here. And what we have seen is that when we are changing the second stage thermal power, so we are putting more fuel in the sequential stage, we are getting some funny thermoacoustic oscillations. And these thermoacoustic oscillations here, they involve two peaks here. This one is the double of this one, and this second heel here is the second mode. So in the end, you have a synchronization phenomenon taking place between the two stages. And so at low second stage thermal power, you have only one peak governing the system. At intermediate thermal power, 27 kilowatts, you have these two peaks, the synchronization phenomenon. And beyond that, you are back to a relay, a low amplitude situation. And what we have seen is that there are two acoustic modes which are involved, one at 70 hertz. This is a kind of quarter wave mode of the system. And this one is at 136 hertz. And this one is more looking like a 3/4 wave mode if we would not consider the area change that you have, the multiple area change that you have all along the combustor. Yeah, and then we looked at the synchronization evolution, the synchronization phenomenon that you get between these two thermoacoustic modes and the statistics of them, and this is yeah, this was very interesting. And it's really synchronization, because if you are looking at these statistics at different locations, you don't have the same patterns here, which is a kind of which is an indication that you have synchronization in there. The sequential combustor has also been used to look at thermoacoustic transient during blow-off of the first stage. So what we've done is we went to a very lean condition of the first stage until it blows off. And this, we did it several times. And so this is a typical time trace that you get if you measure the acoustic pressure inside the combustor. And so you see that there are three phases. One phase where there is acoustic oscillation at one frequency, then you have this very large amplitude burst, and then you end up with the second frequency. So you go at the beginning, you are at 144 hertz, and you end up with 84 hertz. And at the very end here, the first stage is completely extinguished, but the walls of the sequential stage are sufficiently hot that you burn everything as a jet flame in the sequential stage. And this flame is very unstable at 84 hertz. So these are chemiluminescence from the second stage, the first stage, which basically extinguish, and you have this change of frequency. And we found out that this change of frequency is not a change of the acoustic mode, so the spatial distribution of the pressure field, the acoustic pressure field, but just due to the temperature field which is changing. So it's still the first longitudinal mode, but it occurs at another frequency, because at a lower frequency, because the first part of the test read becomes much colder. So it's and the last parts, the last two slides of my presentation are about plasma enhanced autoignition for instability control. So in the frame of my ERC project, which is ongoing, what we try to do is to focus on this sequential combustion system and take advantage of the fact that just at the inlet of the sequential stage, the mixture is already hot and already undergoing autoignition, and therefore it's a nice spot to help to enhance the autoignition process with plasma. And the fact is that, since, as we have seen before, everything is coupled in such architecture, if you have the control, the control on the second flame, you can also control the full feedback. So you can stabilize thermoacoustically your system by only acting on the sequential stage. So, but let's say that there are two challenges in this project. First is to make the active control working, and second, to understand it, and third, to look at how good it works at different pressures. So these are the goals that we have, and especially regarding the understanding of what's going on, we want to isolate thermal and kinetic effects that the plasma, the plasma discharge has on the autoignition chemistry. So this is a picture of one electrode arrangement which leads for this discharge voltage and pulse duration and repetition rate. It gives a volumetric plasma. So you see here the first stage here, then there is a dilution section with the cold air getting inside, and here we are creating a volumetric plasma just before the inlet of the sequential stage. And this is another arrangement with a pin-to-pin that we have done. And you see here a picture of this new sequential combustor that we are using these days. So we have, it's more compact in length, and but the principle is still the same. And I have two movies to show before concluding this talk. The first movie is to illustrate the fact that when we are using this volumetric plasma, we should not conclude that this doesn't work. But in this particular case, the sequential flame is not influenced by this volumetric plasma. And you see it here. This is the intensity of the light intensity, the chemiluminescence from the combustion chamber. So it fluctuates, but it's not changing once the plasma is stopped. So once the plasma was in, I can play the movie again. Plasma was like this, and then there is a flame. But when it stops, let's say the statistical properties of the flame stay the same. I play it again. So here you have the information about the plasma. You can have in mind that the electric, the power that is given to the fluids, the electric power is about 0.1% during this phase compared to the thermal power of the test rig. And so here is the situation where you have the pin-to-pin discharge. So here we have masked it. We have put an optical obstacle because it was illuminating too much the high-speed camera. But you can already see on the time trace that when you stop the plasma, it happens here. Then you have oscillations which starts to develop. And so you have the light intensity which starts to oscillate. And this is the acoustic frequency that you see. And you see the chemiluminescence in the mixing section and in the combustion chamber. So now I play the movie. So now the plasma is going to stop. And the instability is going to start developing. And you see periodically this back and forth oscillation of the flame in the mixing section. And so these are very fresh results, and we are looking at them not only from the thermoacoustic viewpoint, but also we are doing emission spectroscopy and also absorption spectroscopy for measuring temperature in this mixing section, and we are different kind of diagnostics to understand what's going on with this plasma. So these are also statistics of the control on, control off. So when these were modulated at 5 Hz, so anytime it was decaying and then stopped and then growing again. Okay, so I'm at the end of this presentation. My goal was to show you different type of thermoacoustic phenomena that you can have in academic system which resemble to practical applications. and the complexity and the diversity of this phenomena, and with a special focus on the effect of transients and on the architecture of the system. And I thank you very much for your attention, and I hope that I was a bit too long, but thank you for your attention.
Well, thanks so much for the talk. It's very diverse topics and a lot of interesting stuff to cover. We've got a number of good questions in the chat session here from the audience, so I'll just go through them in no particular order from the order that they were received. The first one is actually from myself on page 10. When you're doing the ramping of the airflows, is the burner temperature for each one of your statistical acquisitions the same? For example, if you do one ramp and then another and another and another, with time the burner will warm up. So is the initial temperature on the ramping the same for each case?
Yeah, we waited sufficiently long to initiate the ramps always with the same temperature.
Okay, great.
And this is a very important aspect of the experiment to have confidence in these statistics.
Excellent. Second question is anonymous. It's listed from Huawei Pro to the panelists. On page 24, the flame change from V-shape to M-shape, is it linked to lean blow-off or autoignition of the main flame for a two-stage flame which has a pilot and the main flame?
I would say that we haven't looked, we've done only PLIF in that area, and our movie suggests that the upper branch can find its way in this complex swirling flow to reattach on the outer rim, and that this is supposedly and presumably facilitated by the temperature of the wall. So basically the wall starts to be hotter, and this is helping. So I don't think that this is related to any autoignition phenomenon. So it's just a turbulent flame propagation in the other sides of the of this annular system, of this or axisymmetric system.
Okay, great. Next question is from Younglin Lee. Thank you, Professor Noiray. In an aeronautical engine, can certain relations be built between these flame behaviors and the input from the upstream air compressor?
Yeah, I think that it depends on the burner, and but certainly there are testing which can be done to associate a certain condition to a certain flame topology.
Okay, great. Next question is from Professor Zhu at Princeton. On slide 52, the second stage is an ignition-assisted flame stabilization, and in this case, don't you have a stronger thermoacoustic instability? Is it not better to use forced ignition approach to reduce the autoignition stability?
So, before joining ETH, I spent several years at Alstom, and my experience in industry is that it's not more frequent, or the instabilities are not more frequent or more problematic in terms of amplitude, but they are more difficult to understand. So I would say that a single stage is equally problematic from the thermoacoustic viewpoint if you try to achieve low NOx at high temperature and let's say high performance.
Can I add a comment?
Yeah.
So if you have a second stage that is really in the autoignition mode that rely on ignition delay, and your ignition delay can fluctuate. The flame, the ignition front can move forward and backward, to the side, to the back. That will trigger the instability. The swirling basically that help to bring radicals from the burner gas to stabilize the flame in a certain location, right? So that swirling stabilized flame, mostly they will become stable. When I listen to your talk in terms of plasma, right? You have a volumetric discharge, you have a spark discharge.
Yeah.
The volumetric discharge, you generate a lot of radicals. again, your flame second stage will rely on the plasma-assisted autoignition again. So they will not help you much in terms of reducing instability. But when you have a spark, or when you have a microwave-assisted discharge flame, then that is forced ignition. So you will dramatically reduce the instability if you have a plasma-assisted forced ignition, right spot at the plasma, not waiting for the downstream autoignition. That's my comment.
Let's say that the visible autoignition kernels downstream of the discharge, they are not in the immediate vicinity of the discharge. So I can play the movie again, but they are, let's say, 10 centimeters away from the pin to pin. And we have about 100 meters per second in there. Yeah. And so there is a non-negligible time until which we see, let's say, visually an autoignition kernel. So I don't know if this can be in that situation categorized as forced ignition.
Yeah, anyway, so I think that probably the distance, the shorter is better if you want to stabilize.
But here it works even if in this particular example, it works even if we have quite some distance between the plasma and the root of this autoignition flame.
Okay. Yeah, interesting. Okay, thank you.
Thank you for the question.
Okay, we'll move on to the next question, again from myself. It's on page 58. The flame in the second stage combustor looks quite asymmetric in the top versus the bottom plane. Does that have to do with how the fuel was injected, or is it an artifact of the imaging? And
No, it's not an artifact. It's actually in this previous version of the sequential combustor, we were injecting the dilution air from that place only with a single jet in cross flow, cold air jet in cross flow from the top, which breaks the symmetry of the system, and you end up, and the fuel was also injected in a jet in cross flow manner, which was leading to a non-fully symmetric flame at the outlet. And we made numerical simulations of it, and we have one branch which is richer than the other.
Okay, great. And when you're doing your first stage blow off to look at the thermoacoustics, does first stage blow off actually lead to full second stage blowout, or to some sort of different anchoring mechanism in the second stage only?
A different, let's say, anchoring mechanism, because when we force the blow off, then suddenly we have cold gas which are going to propagate cold air and gas, because the fuel is not cut in the first stage. So we have an ignitable mixture which flows to the second stage and which add up to the sequential stage. And then in that case, for, let's say, 1 minute, the flame stays alive in the sequential stage without the first one being present. And this is also at the same time with a high thermoacoustic limit cycle taking place.
So problematic situation in a real gas
turbine.
Yeah,
very problematic situation, yeah. But in an engine, let's say that this would be very dramatic, that the first stage is extinguishing. But let's say that now that we are thinking of placing more hydrogen into the blend, the idea is to avoid flashback problems in the first stage by going very lean. We also decrease the temperature, which is also good because hydrogen doesn't need the same elevated temperature as the natural gas to autoignite at a certain location. So it's a win-win situation that putting hydrogen in such a system can be done while maintaining the low NOx without having an enhancement of the flashback risk, because the only flame which is stabilized by turbulent propagation against the incoming flow is the first stage flame, and this one we go anyway leaner at So it's a very, very convenient concept for transiting online, let's say, to a significantly different fraction of hydrogen and very large fraction. So they have published last year at Ansaldo paper at the ASME demonstrating that they are really approaching the 100% hydrogen at maintaining the outlet temperature and at NOx values below the emission limits.
Okay, great. We've got about 5 more questions from the audience, so we'll see how many we can get through before the time runs out for today. The next one is again from Yang Qin Li. Professor, could you comment on the difference between the nonlinearity and stochastic behavior here in this work, especially the reason for each of them?
So let's say that flames nonlinearity refers more to how nonlinear will be the coherent flame response to acoustic perturbation. So if you are increasing the acoustic level and you monitor the heat rate fluctuations, and you are increasing this acoustic level and looking only at the time scale of this acoustic forcing, then there are some nonlinearities. And we've seen different flames, and all these flames, they exhibit different nonlinearities, leading to sub or supercritical bifurcation. The stochastic aspect, this is the broadband turbulent combustion noise, which is on the background, and this is making randomness to the system, and explains why the amplitude is not like a pure sine wave, but the envelope of the acoustic signal is fluctuating.
Okay, great. And the next question is from a member of the audience. It's anonymous. What is the pressure of the plasma work, and could it reach the 20 bars for a gas turbine application?
So right now, all the movies that I showed were done with the atmospheric test rig, but we are building a high pressure or an intermediate pressure test rig where we will be able to operate at 8 to 10 bars. So this is will be possible in 6 months from now.
Oh, very impressive.
And so this is let's say one of the key targets to look at how the autoignition enhancement is affected by the elevation by the change of pressure for a given electrode arrangement.
Okay, great. We'll move on to the next question from Yang Qi Fan. Thanks for the great lecture. We have 2 questions. Your model has well predicted the intermittency for the subcritical bifurcation case and the mixed azimuthal mode case. I wonder if your model can also capture the potential intermittency during the switching process from one mode to another with a different frequency. The second question is, can intermittency originate from chaos rather than from the discussed stochastic nature? And can we differ between the 2 origins with the experimental data?
So to the first question, this model is a model which incorporates only one thermoacoustic mode. So it would have to be modified and include a second mode to explain possible switching between 2 modes. And so therefore the formalism has to be is the same, but the order of the model will be increased by the presence of this second mode. But I presume that we can also we could also achieve some kind of predictions. In the second question, the intermittency. There are different types of intermittency which originate either from chaos or from the stochastic nature. And what when I talk about chaos, I have the tendency to reserve this terminology for low-dimensional chaos, which you find in thermoacoustic systems. So there are many very interesting works that have been published on chaotic thermoacoustic behavior, and this chaotic thermoacoustic behavior, they involve let's say, a low number of modes, and the stochastic is more associated with the turbulence in my situation. But then let's say that philosophically you could look at the microscope and consider the turbulence also as a deterministic system. So in that case, turbulence can also be seen as a chaotic phenomenon. But let's say that the number of degrees of freedom is so huge that I prefer keeping the terminology stochastic for the randomness of the turbulence, and keep chaotic only for low dimensional chaotic thermoacoustic behavior.
Okay. Next question is from Praveen K, to all panelists and attendees. In the annular combustor analysis, how is thermoacoustic resonance distinguished from limit cycle? And specifically, how does your pressure time series look during the thermoacoustic resonance? Wouldn't the high temperature of the exhaust of sequential stage combustion pose problems for the turbine stage, or is the turbine further away?
Okay, so first, regarding the resonance, let's say that there are some ways to distinguish between the two by looking at the PDF of the acoustic envelope amplitude, and I'm trying to go to the slides. But let's say that here, if you look at the PDF of the acoustic pressure at a certain location, the PDF will be a Gaussian-like PDF, and this will be very typical of a resonance. You can take just a simple mass spring system, mass spring damper system, and force it with white noise, and look at the histogram of the response of this mass spring damper system. This will be a Gaussian-like behavior. While if you are taking the histogram of the acoustic pressure in that situation, then you will see two hills. So you will see a bimodal behavior. So this will be the distinction that you can make by doing data analysis. And wouldn't the temperature of the exhaust both, or from an operator? Yeah, the exhaust of, when you are playing with a turbine, you try to maximize your temperature at the turbine inlet under the constraint that the turbine can survive, and under the second constraint that you are not making too much NOx. But let's say that from a thermodynamic cycle viewpoint, high temperature is good for efficiency and power. And so let's say that this is not related to my research. This is more an engineering aspect of the problem.
Okay, we'll move on to the next question from Balasandaram Mohan. In sequential combustion, are you able to suppress the instability by rearranging the gap between the flames? I assume that means the first and the second stage flames.
Yes. So this is this has a very important effect, because it will change the time delay between entropy waves traveling from the first and impinging the second stage flame. So this can have a very strong effect in the overall thermoacoustic coupling. And if you change the distance, you will have an effect on the thermoacoustic instability. But let's say that here, once you have a combustion, a burner is more, let's say, easy to redesign than a full combustion chamber. So once you are stuck with a certain distance between your first and second stage, you have to find other ways to eliminate the instability, usually.
Great. Next question's from Jay Gore. Is the M-shaped flame only formed when the annular wall is hot? And to follow on, can the wall temperature be used to control the heat up, to control the jump in the heat release rate?
So for this mixture this was pure natural gas and air. You really need to go up in thermal power. So it's not only a question of adiabatic flame temperature. So it's not a question of equivalence ratio. It's really a question of thermal power. And this is basically because you have the hot gas a bit downstream of the root of the flame, which are heating up the quartz sufficiently high thermal power. So yes, you can get only the M flame if the quartz is sufficiently hot. And the control of this temperature, we didn't have the possibility to control it for this particular setup.
The next question is again from Bala Sandran, and it's sort of a related topic. On slide 24, the intermittent transition caused by wall confined or wall temperature with the ceramic wall, have you observed similar features?
We don't have a ceramic variant of this setup. We have only the quartz tube.
Okay, maybe something to think about for the future.
But I think that's, yeah, if you change the thermal resistance of the wall, then you will affect clearly the flame topology, and therefore you will affect this thermoacoustic behavior.
Okay, I think we're down to the last two questions in the chat, and then we'll tie it off. So apologize to anybody who has further questions. The next question is from Hasti. Great talk. Thanks for that. The combustor operating condition changes the hydrodynamic features such as recirculation zones, precessing vortex core dynamics, coherent structures, etc. I'm wondering if you have looked at the role of these features and their contribution to thermoacoustic instabilities.
For this particular case, we haven't done any particle image velocimetry. So it's indeed correct, and I should have mentioned it as a possible mechanism to get the M flame. Basically, if the hydrodynamic is significantly changing when the air mass flow is changed, then this is adding up onto the thermal effect of the boundary condition.
Okay, and the final question from the audience, again, an anonymous contributor. Thanks, Professor. Do you find there exists links between thermoacoustic and convective time delay in your research?
Yes, there are many convective time delays which are very important in all the systems that I talked about. Time delays at the burner level for the fuel, from the fuel injection to the flame, time delays between the flame and the outlets, time delays between the flame of the first stage and the second stage. All kinds of time delays are crucial to be accounted for when you are modeling this type of systems with the intent of being predictive. So when you are trying to do network modeling, thermoacoustic network modeling of the system, not the oscillator description, this is not allowing you to do some predictive aspects.
Okay, great. So we managed to cover all of the questions from the audience, and we'll close out the talk here. If the audience would like to turn on their cameras and thank the speaker, we're free to do so. And yeah, really appreciate it. It's been an exciting talk.